Hello everyone, welcome to the third video of our indexing playlist. In this video, we are going to see about MV search trees, B-trees and B+Trees. We lead to this topic after we have studied about the multi-level indexing. So now let's understand the MV search trees and how they are related with multi-level indexing. Let's see that. So to understand the MV search tree, we should know what are binary search trees. So it is a simple concept that whenever there is a root node, binary means that it can have only two children at max. So this has having the left children and the right children, at most two children. Okay, again there is a left children and the right children. Every node can have only at max two children. This is the first point. And the second point is all the values that are smaller will go to the left hand side, and all the values that are going to be large that will go to the right hand side. So let's say this is 90 is our root node, and the 70 will small, then it will go to the left hand side. Again the value of 40 is going to be small, again the left hand side. Value is going to be 75, again smaller than 75 is smaller than 70, then it will go to the left hand side, but it is going to be greater than 70, so it will go to the right hand side. Same with these elements as well, 100 and 120. Now instead of having two children, I need to have more children in our tree, so we will lead to the three-way search tree. Okay, now what I am saying, instead of having two children, I need to have one more children. So let's see how we can achieve it. So what did I do? There is a, let's say, a root node 20 and 40. Previously there was only one value, that was 90, but now there are two values in our root node, 20 and 40. And now what I am saying, if the value is less than 20, it will go to the leftmost child. If the value between 20 and 40, it will go to this 30. If the value is greater than 40, it will go to the rightmost child, that is 50 and 60. This is an example of three-way search tree. So I also want to make you understand that if there are three children, so the root can have at most two elements. Okay, then only it can be divided into three, I guess. Okay, let me just make you understand it one more time. Let's say if this element has only one value, so either a value can be smaller and the value can be larger. Okay, this is our binary search tree. But let's say if the divided, okay, let's say we are having two values that are two elements, then only we can say that there can be a value in between as well. So this is an example of three-way search tree and can have at most two elements in our parent. This is the example of M-way search tree, or you can say three-way search tree. So let's say if we want to have four children in our tree, it should be something like that. Our root element will divide it into three halves. This value is going to be smaller than this particular value. After that, this section is going to say I will have the value between these two elements. This element will say I will have the value between these two elements, and this element will say I will have the value greater than this last element. I think this is also clear to you. This is our four-way search tree. Now let's see how it is connected to indexing. So in the previous video, we have studied about the multi-level indexing, and can you just see this particular section that I'm mentioning? Here, can you see this thing? That this is an element that is having divided into two sections. This is section 1, this is section 2, and having three childs. Okay, this is the smallest one, this is the middle value, and this is the greater values. Can you think that this particular thing is giving the feeling of M-way search tree? So now let's see what is the actual data that we store in M-way search tree in the case of indexing. So to make you understand, I draw one four-way M-way search tree here where I am having four children, and there will be a root node with having three keys. Okay, this point is very clear. This particular node will have the value smaller than this key. This particular node will have the value between these two elements. This particular element will have the value between these two elements, and this particular element, the last one, will have the value greater than the key 3. I think this part is very clear to you. Now what we want, now let's understand what's the data they are going to store. So this key 1 is going to store the two things. The first thing that it is going to store the value that is related to the child. Okay, child elements. Okay, because they are pointing. What I mean by this, so let's say the key 1 is the value is going to be 10. Okay, in the key 1, value is going to be 10, and someone is searching for 9. So it will simply say go to my child node, because value is going to be smaller than, let's say, 8. Okay, go to my child node. Let's say the value is going to, let's say key 20 is going to be 20. Okay, let's say key 3 is going to be 30. If someone is searching between, let's say, 15, so it will say go to this particular node. Let's say if someone is searching for 20 or 30, let's say someone is searching for 25, go to here. Let's say someone is searching for 38, go here. what I want it, let's say someone is searching for 10. In that case, what will happen? When someone will reach to this key 1, okay, so this key 1 I told you contains two values. The first value is going to be of the child node. Second thing that is going to be contain the actual value pointer, or you can say block address. I think this is particularly fine. We have studied about the block address in our previous videos as well. So the key 1 is the 10th row. So we are going to store the actual block of this 10th index that can be, so we have studied about the track and sectors. So we are going to say 2, 3. So our disk will rotate and will directly reach to 2, 3 and we will reach to that point. Okay. So this is how the data is going to be stored in our MV search trees. Now let's move to the problems that are in MV search tree. There is only one problem in MV search tree, that there is no particular rule to create an MV search tree. So let's say if there is a value 100, so what we can do, let's say there is new value coming to 100. So what we can do, either we can insert it here, okay, or we can make a new row because on the right hand side. Let's say there is new value coming 300, either we can insert it here, or what we can do, we can make a new row. So there was only one issue, that there is no particular method to create an MV search tree. You can do whatever you want. This is the only problem with MV search tree. So we will move to now B-trees. So to solve this problem, we will understand the B-trees. So B-trees are nothing but a simple MV search tree with some specific methods of creation. Okay. So B-trees are nothing but a simple MV search tree with some specific methods of creation. Now so now let's understand what are these methods. So first pointer is going to be that at least m by 2 entries must be there in a children. We are going to say that at least m by 2 entries should be there in a children. That is our first point. Second point is root can have minimum 2 children. Root should have the minimum 2 children when it is going to be not a parent node, the most parent node. Otherwise the root should have minimum 2 children. After that, all the leaves are at the same level, and it should be build a bottom approach. Okay, we are going to see when we are going to construct the B-trees. I think these are the 4 methods that you have to follow. Let's see them and let's try to make our simple B-tree and we will understand it. So let's say I want to make a B-tree of these value 10, 20, 30, 40, 50, 60, 70 and 80. I want to construct it. So the first value is going to be 10. Okay, this is a parent node, so we can have one value in our root. This is our 10. After that, we'll move to the second one, that is going to be 10, 20. Okay, we inserted it. M is equals to 3. That means that we are going to make our 3-way search tree. Okay, so 10 equals 10 and 20. Now what will happen when we get a new value 30? So we cannot go to this section. No, we are going to make a MV search tree that we need a 3 children, so our root can have only 2 elements in our top. So what we are going to do, we have to go for this section, that we are going to divide this MV search tree in this 20, 10 and 30. I think this is clear. After that, what we are going to do, we are going to insert 40, 20, 30, 20, 10, 30 and 40. After that, what will going to happen, we will move forward. Now the insertion is going to be of 50. Where we are going to insert the 50, we are going to insert 40 will go above. In that case, 20 and 40, 10 is here, 30 is going to be between the 20 and 40, so 30 will come here. 50 is greater than the 40, so 50 will come at the right hand side. Now we are going to insert the 60, so 20, 40 is on the top, 10 is staying, 30 is okay, 50 and 60. Again, let's say when we are going to insert 70, again it is going to divide. Okay, 40 will go to the top, then there will be 20, then there will be 60, 50, 70, 30 and 10. So I think this B-tree is not that tough, and this insertion is pretty simple. And I also told you that what are the values that they are going to store. The value of the child pointer, and the second value that they are also contain is going to be related to that the actual value of the block. So that if like someone is searching for the 40 index directly, we can directly reach to the block. If let's say someone is searching for the 30, so it will go to the, let's say 40, then it will say that is a less than 40, it will go to the 20 direction, and when it is reached to the 30, it will go to the 30 direction. This is the simple example of B-trees in our indexing. Now let's understand one more thing. What are the B+Trees? B-trees and B+Trees are similar to each other. What we are going to do, that when we are going to reach to our child, or let's say to the leaf node, in that case what we are going to do, we are going to make a linked list here. These all the elements are going to be connected in our leaf node. This is an example of our B+Tree. Our all the leaf nodes are also going to be connected with the help of a linked list. Okay, here the tree was connected like this. Here the tree is also similarly connected, but we just also make one linked list at the leaf node. And there is second thing that we have to do, linked list we have covered, and the second thing we have to do is, in our B+Tree, all the elements are going to be present in our linked list. So our linked list is going to be look like something like this: 10, 20, 30, 40, 50, 60, 70, 80. So it means that in our linked list, all the elements that are in the leaf nodes are going to be present, but all the elements that are not in our leaf node. So it means that 20 is going to also be present in our linked list. 60 is also going to be present in our linked list. 740 is also going to be present in our linked list. 80 is also going to be present in our linked list. All the elements of the tree are going to be present at the leaf node. This is the first point. Second point is that they all are also going to be connected in a form of a linked list. So this B+Tree is solving the two problems. Okay, let's go above and let me just tell you the two things again to this diagram, and you will understand it. These are the elements and these are the elements. I think this is very clear that this is a MV search tree. This is the MV search tree. This is clear. And this, you know that this is an example of a B tree as well, because they are following the pattern. Okay, this is clear. But this is the only problem in a B tree, is that these elements are not connected. This element is not connected with this element. This element is not connected with this element. This element is not connected with this element in our B tree. But B+Tree is solving that problem with the help of linked list that we are managing at the leaf node. So can we say that this is a linked list that we are managing at the leaf node? The linked list that we are managing at the leaf node is acting as a dense index. So this is a problem that the B+Tree is solving. So in interviews, like someone asks you which tree that you are going to use in our indexing, you can say B-Trees and B+Trees, and the B+Tree is going to be the most appropriate answer, because B+Tree is going to also maintain a linked list that is going to solve the problem of dense indexing. This is all about B-Trees and B+Trees. In the next videos, we are going to study about hash indexing. So for that, let's meet in our next video. Thank you for watching me, and bye bye.